So now that we have a basic idea of how to write, how to interpret, how to balance chemical equations, and also how to classify them, we're going to take a look at probably the most important use of a chemical equation, and that is extracting the relevant information and then using that to solve problems. And that is encompassed in a concept known as stoichiometry. All right, and all this means is using the information from your balanced chemical equation. So in order to do stoichiometry, you you absolutely need your equation to be balanced, and then we can use the information that we get from it. So let's take a look at an example and show you what this actually means. So we looked at this equation before. So we saw hydrogen reacting with oxygen to produce H2O. And then we balanced the equation by sticking a 2 in front of um, the H2O and the hydrogen, and then we had a 1 here in front of the oxygen. So when we use these coefficients to balance the equation, this actually gives us, well, they give us the coefficients balance the equation to make sure we don't violate the law of conservation of matter. But what they also do is they give us a ratio of the reactants to the products. And that ratio is nothing more than a mole ratio. So in other words, another way I can look at this equation is as follows. I can say, based on this balanced equation, and I can say that 2 moles of H2, hydrogen, react with 1 mole of oxygen, O2, to produce 2 moles of H2O, right? And these mole to mole, or these mole numbers, are nothing more than the coefficients that we use to balance the equation, right? So yes, we use the coefficients, we don't violate the law of conservation of matter, but then it also gives us these mole relationships. And that's important because we can use those relationships to go between one reactant and another reactant, or a reactant and a product, depending on what it is that we're trying to find. You can think of the mole to mole ratio kind of analogous to like a recipe that you would use to make something, right? To make a dish or a sandwich or something. So for example, we can say, to make one sandwich, you need 2 slices of bread and you need 1 slice of cheese, right? So a very simple sandwich. Same thing here. In order to make 2 moles of water, we would need 2 moles of hydrogen and 1 mole of oxygen. It's very similar if you look at it from that perspective. Now, let's take a look at how we can use that information. So using that balanced equation, okay, and this is also very important. You want to make sure that your equation is balanced before you start doing any stoichiometry. So we have 2H2 reacting with O2 to produce 2H2O. Okay, so if you start with, let's say 10 moles of oxygen, okay, how many moles of water can be made? Okay, and this is at the heart of every stoichiometry problem that you're going to see. So you have your balanced equation, right? That's the most important thing, and we have that. We've balanced it several times already. And now we want to organize the info that we're given. So we're told that we have 10 moles of the oxygen. So this is the thing that we're starting with. And we want to relate it to, we want to figure out how many moles of water. So this is the other thing now that we wanted to to relate it to. So these two things we want to relate to each other. Okay, so you want to relate the oxygen to the H2O, and the relationship between them is nothing more than those coefficients, which are a mole to mole ratio. So we're going to use the coefficients to relate them. Okay, and according to this balanced equation, it says that 1 mole of O2 produces 2 moles of H2O, right? So I'm writing this as an equality so that I can turn it into two conversion factors. So now I have 1 mole of O2 over 2 moles of H2O, right? So again, when you have an equality, whether it's an equality like this or within the metric system, doesn't matter. You can turn it into two conversion factors. The other one here is just simply flipping the first one. So 2 moles of H2O for every 1 mole of oxygen. So now, right, I have these relationships that I extracted from the mole to mole ratio that I got from the equation. If I'm starting off with now 10 moles of oxygen, so we're starting with 10 moles of O2, okay, put that over 1. If I want to end up with moles of H2O, I'm going to pick the conversion factor that has the moles of H2O on top. So 2 moles of H2O for every 1 mole of O2. Moles of O2 go away, cancels out, and we end up with 20 moles of water. Now, you probably could have done that in your head by looking at the ratio here, right? So if you have a certain 1 mole of this, you need twice as many, or you're going to make twice as many of the H2O, right? That's intuitively, you can see that from the equation, but this is how we use the coefficients to incorporate them into these sorts of calculations. All right, and if you can do that, you can do stoichiometry, because all the other types of things that we're going to see are just layers that we add on top of it. In order to do it, though, we need the balanced equation and we need those coefficients. Those coefficients give you the mole to mole ratio. All right, if we look at another example using that same equation, let's say if you start with 4.5 moles of H2, okay, how many moles of water can be made from that same equation? Well, now we want to relate the two things that we have, so the H2 to the H2O. Okay, we're not concerned about the oxygen now. All right, so if I look at the H2 on the H2O, the relationship there is 2 moles of H2 to 2 moles of H2O. All right, so I can say 2 moles of H2 is equal to 2 moles of H2O. I have now my equality. I have my two conversion factors. Put one over the other. And then flip it to get the other conversion factor. Okay, so I have the things that I can use. So now if I'm starting off with 4.5 moles, that's what I'm given. So 4.5 moles of H2, I want to get or end up with moles of H2O. I'm going to pick this conversion factor, stick it in here. So now I have 2 moles of H2O for every 2 moles of H2. So that goes away, and 2 cancels with the 2, so I get the same number of moles, 4.5 moles of H2O. Again, something that you could have probably predicted based on the fact that there was a 2 to 2 ratio, which is the same as a 1 to 1. So whatever number of moles of the H2 I start with should produce the same number of moles of the H2O, and this is why. So I should get 4.5 moles of water. So the mole to mole ratio, and this is the main part of this section, the mole to mole ratio, okay, allows us to convert or to relate anything in an equation to any other thing in that equation, whether it's a reactant to a product or a reactant to another reactant or a product to a product. Okay, this is the key thing that we're using in any stoichiometry problem. That's a mole to mole ratio. Where do we get that ratio from? These are simply the coefficients from the balanced equation. Okay, if you keep that in mind, in every stoichiometry problem you do, that's at the heart of every single one of them that you're going to do. Okay, so when we look at the next section, we'll see how we can add another layer to this, because generally in the laboratory, you don't measure things out in moles, right? You measure things out in grams or milliliters or even other units. How do we get to moles in the first place to be able to use our balanced equation? That's what we'll take a look at next.